Since ancient times, humans have always longed to learn about the universe and the nature of existence. In ancient civilizations, the universe was envisioned in a dualistic model, heaven and earth. Many believed that the sky was a giant circle, while the earth was square and supported by invisible pillars. However, with the development of science and technology, these views were gradually replaced by more accurate models. Astronomers have proven that the Earth is not flat, but spherical, and the universe is not static, but constantly expanding. Thanks to these advances, humans have increasingly understood their place in the vast universe. However, there are still many unanswered questions, causing us to constantly explore and pose new hypotheses about the true nature of the universe. The holography principle is a concept in modern physics that suggests that the universe may be just a three-dimensional image projected from a two-dimensional surface. The idea is based on the principle of holography in optics, a special technique that records and recreates a three-dimensional image from a two-dimensional image. Holography was invented in 1948 by physicist Dennis Gabor, who received the Nobel Prize in 1971 for this work. A special feature of holograms is that information about a three-dimensional object is completely encoded on a two-dimensional surface. When illuminated by a suitable light source, the three-dimensional image will appear clearly. This raises a surprising hypothesis. If the entire universe also works according to this principle, then the three-dimensional space we are observing is actually just a reflection from a more distant 2D surface. This hypothesis has important applications in theoretical physics, especially in explaining complex phenomena such as black holes and quantum mechanics. One of the big problems in modern physics is how to reconcile Einstein's general theory of relativity with quantum mechanics. The holographic principle suggests that, instead of trying to combine two theories in three dimensions, we can describe the universe using information stored on a two-dimensional surface. This helps scientists resolve many paradoxes and opens up a new way of looking at the nature of space, time, and the universe we live in. The holographic principle makes a startling observation. The three-dimensional, 3D reality we observe may simply be a projection of two-dimensional 2D data. This means that all the information about the three-dimensional universe could be encoded on some distant two-dimensional surface, similar to the way a hologram stores a three-dimensional image on a two-dimensional film. This equivalence has profound implications for theoretical physics. If the universe really works according to the holographic principle, then every three-dimensional phenomenon, from galaxies to planets to ourselves, can be viewed as a form of information encoded on a two-dimensional surface at the edge of the universe. This helps solve many difficult problems in physics, especially in reconciling general relativity with quantum mechanics. Although the hypothesis has not been fully proven, many scientists believe it could provide a new approach to understanding the nature of reality. If true, this would change the way we perceive the universe and our place in it. The holographic principle comes from studies of black holes, especially the problem of information conservation. According to Stephen Hawking, black holes emit radiation and gradually disappear, raising an important question. Where does the information about objects falling into black holes go? If the information is destroyed, this contradicts the principle of information conservation in physics. To solve this problem, Leonard Susskind and Gerard Hooft proposed that information does not disappear, but is stored as a two-dimensional trace on the surface of the black hole, known as the event horizon. When radiation is emitted, it carries this information with it, ensuring that the data remains intact. This suggests that the entire universe may work in a similar way. What we perceive as 3 dimensions is actually encoded on a 2-dimensional surface at the edge of the universe. This discovery not only solves the black hole information paradox, but also provides a new approach to understanding the nature of space, time, and gravity, opening up a new direction in modern physics. In the 1970s, physicist Jacob Bekenstein calculated that the entropy of a black hole, a measure of how disordered a system is not proportional to its volume, as it is for ordinary matter, but is proportional to the 2-dimensional surface area of its event horizon. This led to a surprising finding. A 3-dimensional object, such as a black hole, can be described entirely by information on its 2-dimensional surface. This discovery provided strong support for the holographic principle, as scientists realized that not only black holes, but the entire universe could follow this principle. This means that all the information about our 3-dimensional world could be encoded on a giant 2-dimensional surface at the edge of the universe. This idea is not just an abstract hypothesis, but also plays a key role in the study of quantum gravity, the field of physics that seeks to combine general relativity with quantum mechanics. If this principle is proven, it would completely change the way we understand the nature of space, time, and reality. The connection between the holographic principle and string theory. String theory is one of the most powerful models for unifying gravity with quantum mechanics. However, one of the most important breakthroughs in this field came from physicist Juan Maldacena in 1998. He proposed a hypothetical universe in anti-de Sitter space, where gravity could be described by a quantum system in 2 dimensions. This idea suggests that all the information about the 3-dimensional universe could be encoded on a 2-dimensional surface, similar to how a hologram contains all the information about a 3-dimensional object on a single 2-dimensional plane. This helps explain many important questions, including how information is preserved in black holes. By linking the holographic principle with string theory, Maldacena has created a powerful tool for studying quantum gravity, opening up a potential path to unifying fundamental theories in physics. Experimental evidence for the holographic principle. Despite the theoretical advantages of the holographic principle, there is no conclusive experimental evidence that our universe is a holographic projection. However, physicists have been looking for signs that this hypothesis can be tested. One way to test this is to study the limits of information that space-time can hold. If the universe really works according to this principle, then the amount of information in a 3-dimensional space must be limited by the 2-dimensional area surrounding it. Fermilab physicist Craig Hogan has proposed an experiment using the Holometer, a supersensitive laser device, to look for tiny fluctuations in space that could be evidence of a holographic quantum structure in space-time. Scientists have also studied how information is stored in the cosmic microwave background radiation, a remnant of the Big Bang. If this principle is correct, it could help explain a number of issues in cosmology, including the nature of dark energy. Searching for experimental evidence for the holographic principle. The holographic principle is a revolutionary hypothesis that the 3-dimensional universe we experience may simply be a projection from a 2-dimensional surface. While the theory solves many problems in modern physics, a major question is whether there is any experimental evidence that can confirm or disprove the hypothesis. Many physicists have been searching for verifiable signs that our universe really does operate according to this principle. One of the most important efforts to test the holographic principle came from the work of Craig Hogan at Fermilab. He and his colleagues developed a special device called a Holometer, designed to detect tiny random fluctuations in the fabric of space-time. If the universe is indeed a hologram encoded from a 2-dimensional surface, then space-time may have a quantum limit at the microscopic level. In the same way that digital information is limited by the resolution of a screen. Holometer uses powerful lasers to measure these fluctuations, hoping to find signs of the quantization of spacetime. If this unusual fluctuation is detected, it could be evidence that our universe actually operates according to the holographic principle. In addition to Holometer, a number of other studies have also sought to test this hypothesis through the phenomenon of quantum entanglement. In quantum mechanics, quantum entanglement is a phenomenon in which two particles can be linked to each other regardless of the distance between them. What's special is that if the universe is indeed a hologram, then the quantum entanglement model could help test how information is stored on a two-dimensional surface and reflected in three-dimensional space. Some physicists have performed calculations to see whether the predictions of holographic theory match current models of quantum entanglement. If they do, this could be a sign that the hypothesis is valid. In addition, several other research groups have also tested the hypothesis by analyzing the cosmic microwave background, CMB radiation, the remnants of the Big Bang. Some scientists have suggested that if the universe is indeed a hologram projected from a two-dimensional space, then fluctuations in the background radiation could have distinctive signatures that reflect the holographic nature of space-time. However, so far, there is no strong enough evidence to conclusively support this hypothesis. Although experiments are still ongoing, finding experimental evidence for the holographic principle remains a major challenge. If this can be verified in the future, it could completely change the way we understand reality and the universe. Is the universe a projection or a simulation? Some scientists, including philosopher Nick Bostrom, have expanded on this hypothesis by asking, if our universe is a projection, could it simply be a simulation created by an advanced civilization? Bostrom argues that if technology is advanced enough to simulate a complete universe, then it is likely that we are living in a simulated reality without knowing it. Although there is no conclusive evidence for either hypothesis, research into the holographic principle and the possibility that the universe is a simulation continues to be of interest, as they could provide deeper insights into the true nature of the universe.
Our universe is an immense space with a scale far beyond human imagination. The number of stars in the universe is estimated to be greater than the number of grains of sand on all the beaches on Earth, combined a number that is difficult for humanity's understanding to grasp. However, contrary to the impression of a crowded universe, the reality shows that the universe has an incredibly low density of matter. If each star were scaled down to the size of a grain of sand, the average distance between these grains would be around 8 kilometers, equivalent to the height of Mount Everest. When converted to actual scale, this distance corresponds to 5 light years, a distance that current human technology cannot overcome. To put this into perspective, NASA's Parker Solar Probe, fastest spacecraft ever built by humanity, would need about 7,000 years to travel from Earth to the nearest star. Notably, this is just the distance to one star. The nearest galaxy is hundreds of thousands of times farther away. Faced with such immense distances, humanity seems trapped in an invisible cage formed by the laws of physics, restricting all efforts to explore the universe. However, humanity has not given up hope. While science and technology have their limits, imagination does not. Based on a combination of physical theories and imagination, we can envision a spacecraft capable of taking humanity to the farthest reaches of the universe. This journey promises to be filled with countless wonders. What will happen when we travel aboard such a ship? And what awaits at the end of the universe? Prepare yourself for this adventure. Our imagined spacecraft is designed to far exceed what humanity can currently build. The ship has the ability to accelerate steadily at 10 m, an acceleration slightly higher than gravity, about 9.81 m, ensuring the safety of passengers. After 40 seconds from departure, the spacecraft's velocity reaches 400 mph and continues to increase. We assume that this ship could accelerate indefinitely over long periods, something not yet possible but entirely imaginable in this scenario. In addition, the spacecraft is equipped with the ability to withstand all types of radiation and potential collisions during its journey. Inside the ship, thanks to an acceleration equivalent to Earth's gravity, passengers will not experience weightlessness as depicted in science fiction movies. Daily activities proceed as usual. Although the initial phase seems slow, the spacecraft's speed will quickly accumulate. After about 2.5 hours, the ship will have passed the Moon. After a day and a half, Mars will be left behind. Remarkably, just 3 weeks later, we will have exited the solar system, reaching a speed of more than 65 million kilometers, equivalent to 6% of the speed of light in a vacuum. However, this speed is still not enough for the effects of special relativity to become significant. This information is crucial for the next phase of the journey. Immediately after leaving the solar system, our next target is the nearest star to Earth in the universe, Alpha Centauri. If you wish to learn more, you should research this star system. The light from Alpha Centauri grows increasingly brighter, while the Sunday is now just a faint dot outside the window. Over the next year, there will be no major events, except that the spacecraft's speed will continue to increase each day. Currently, direct communication with friends and family on Earth is impossible due to the lengthy time it takes for radio waves to travel. However, the sense of loneliness is somewhat alleviated by the news updates covering current events, culture, sports, and scientific discovery 7, though they occasionally come with some delays. After 15 months from departure, our crew celebrates the milestone of surpassing the distance of 1 light year. This is an astonishing fact. As of now, we have covered a quarter of the distance to Alpha Centauri. In terms of time, we have completed a third of the journey as the spacecraft's speed continues to increase over time. Another significant milestone we've achieved is that the Lorentz factor of the spacecraft has now surpassed a value of 2. The Lorentz factor, according to Wikipedia, is a quantity used to describe the curvature of space-time, directly proportional to the speed of the object. The formula to calculate the Lorentz factor is gamma is 1 divided by the square root of 1 minus the square of the object's velocity, divided by the square of the speed of light. In this formula, J1, Ma3, gamma, is the Lorentz factor, V is the velocity of the object, and C is the speed of light in a vacuum. As the speed approaches the speed of light, the Lorentz factor increases, leading to the special effects described by Einstein's theory of special relativity. 1. Length contraction. From the perspective of an outside observer, the length of an object in the direction of its motion appears contracted. 2. Time dilation. Time inside the spacecraft passes slower compared to time for an observer on Earth. In this case, the time that has passed since the ship's departure, according to Earth's clock, is 15 months. However, the crew on board experiences less time due to time dilation. Currently, the spacecraft's speed has reached 87% of the speed of light. If the acceleration continues as it is, the observed speed will reach its maximum in the next 45 days. However, according to special relativity, no object can travel faster than the speed of light. Even though the spacecraft's speed approaches light speed, an outside observer will only see the maximum speed as the speed of light. To make this clearer, let's compare it to a car. If you are driving at 90 km per h and chasing another car moving at 100 km per h, you will observe that the other car is moving away from you at only 10 km per h. But when chasing a beam of light, its speed remains fixed at 300,000 km per s, regardless of how fast or slow you are moving. This phenomenon occurs because the speed of light is a constant, independent of the motion of the observer or the light source. Therefore, to maintain the constancy of the speed of light, time and space must adjust. This adjustment is expressed through the Lorentz factor, and is the reason why time and space on our spacecraft differ from those on Earth. An observer on Earth will perceive our journey as taking longer than what the crew on board experiences. This is a direct demonstration of the effects of special relativity on this interstellar journey. Additionally, when the Lorentz factor exceeds a value of 2, it begins to affect how the acceleration of the spacecraft is perceived from Earth's perspective. An observer on Earth will notice that the spacecraft is no longer accelerating at 1g, but its speed increases more slowly until it approaches the speed of light. Therefore, when we say nothing is faster than light, we are speaking from the perspective of an external observer. However, for you and the crew on board, everything proceeds as normal. The spacecraft continues to accelerate, and in fact, it has already exceeded the speed of light from the perspective of the crew. This becomes more apparent when you look outside the window. The Sunday's light quickly fades, as if we are being separated from the rest of space-time. However, infinite acceleration is not a feasible idea, as our energy source is not infinite. At some point, the spacecraft will need to decelerate to stop and land, which will also require an enormous amount of energy. We can calculate to decelerate the spacecraft with an acceleration of -1g, decreasing the speed by 10 m/s every second until it comes to a complete stop. To do this efficiently, the deceleration process will begin once the journey reaches halfway. Returning to the initial journey, the first destination is Alpha Centauri, which is 4.4 light-years away from Earth. A light beam from Earth takes 4.4 years to reach there, but aboard the spacecraft, only about 3.5 years will pass. This does not violate relativity because, from Earth's observation, the actual journey has lasted 6 years since the beginning. You will have a few weeks to explore Alpha Centauri before heading back. The return process is similar, accelerating with 1g until the halfway point, then decelerating with -1g. Upon returning to Earth, the total time for you will be about 7 years, but for people on Earth, the journey will have taken 12 years. This is an impressive duration for humanity to reach the nearest star. Another important detail is the timing of deceleration, which occurs 2.2 light-years from Earth, around 1.8 years after departure, according to the spacecraft's time. At that point, the spacecraft's speed reaches 95% of the speed of light. However, after reaching Alpha Centauri, a heated debate occurs among the crew members. Eventually, everyone decides not to land on Alpha Centauri but to continue the journey, using the spacecraft to explore further into the universe. The new journey is divided into 4 phases: acceleration on the way out, deceleration on the way out, acceleration on the way back, and deceleration on the way back. The next goal is to travel beyond a distance of 30 light-years to escape the boundary of the local interstellar cloud, the region where the solar system is located. To complete this journey, the total time on board the spacecraft will be 133.4 years, including both the outbound and return trips. However, upon returning to Earth, our descendants will be nearly 70 years old, leading to strange reunions like those in the movie Interstellar. After crossing the 30 light-year boundary, we will enter a region of space known as the local bubble, a structure that extends over 300 light-years. To complete the round trip through this region, the spacecraft will need an additional 22 years on board. However, when we return to Earth, 600 years will have passed. Faced with such vast distances and the passage of time, we may wonder whether those remaining on Earth will still remember that 600 years ago, a crew departed from the planet to explore the vast universe. 22 years aboard the spacecraft is no short time, but 600 years on Earth would bring a completely unfamiliar world with changes beyond our imagination. Although age will inevitably increase after such a long journey, the crew can continue to contribute to a further mission. A potential goal could be to leave the Orion arm of the Milky Way. With the spacecraft's continuous acceleration, a round-trip journey to the edge of the Orion arm and back would take only 41 years aboard. The journey would be divided into 4 phases: acceleration on the way out, deceleration on the way out, acceleration on the way back, and deceleration on the way back. The spacecraft reaches its maximum speed in the 8th year, completing the acceleration phase on the outbound trip. After about 6.5 years aboard, a strange phenomenon will appear outside the window. A region of bright red light gradually becomes visible. Initially, it may seem like an illusion or a visual issue, but in fact, this is due to the Lorentz factor reaching 650. The cosmic microwave background radiation is shifted into the visible red light spectrum, creating this unusual scene. As the spacecraft reaches maximum velocity, the space outside seems to glow red. It feels as though the spacecraft is attracting the attention of the universe itself. Beyond the edge of the Orion Arm, the next goal could be the edge of the Milky Way, over 100,000 light-years from Earth. The round-trip journey would take 41 years aboard the spacecraft. When returning to Earth after this journey, the crew members will be over 60 years old, while on Earth, millions of years will have passed. After 1 million years, society and technology on Earth will have changed beyond our current imagination. Due to limited living space, large space stations in orbit may become an alternative. 3 potential models for future space stations include: 1. Spherical settlements, capable of generating artificial gravity suitable for populations ranging from 10,000 to 1 million people. 2. Torus settlements, large circular designs with living and agricultural areas. 3. O'Neill cylinder settlements, the largest design featuring large windows to let sunlight in, creating Earth-like landscapes. People would live on the curved surface and could grow crops there. Radiation will be blocked by polyethylene shields or electromagnetic fields, similar to how Earth's magnetic field protects us from cosmic rays. Technology supporting life in space includes: 1. Oxygen production. Technologies like water electrolysis and the conversion of CO into O are being developed to help sustain life on planets such as Mars. 2. Compact nuclear energy. Small-scale nuclear fuel cells 12 times 18 centimeters can provide long-term energy for space settlements or interstellar journeys. When humanity returns to Earth after millions of years, the world will have transformed in unimaginable ways. Technologies and off-planet settlements may have become the norm, allowing humanity to expand its living space and maintain long-term existence in the universe. NASA is utilizing 3D printing technology to develop lunar habitats, which are expected to be completed by 2040. The primary material for construction will be lunar dust, and these homes will be designed to be safe for human habitation. In 2022, NASA successfully conducted the Artemis 1 mission, the first test flight of the Artemis program aiming to return humans to the Moon. The spacecraft orbited the Moon and returned safely to Earth. 1. Artemis II, taking place in November 2024, will send 4 astronauts into lunar orbit on a 10-day mission. 2. Artemis III, initially planned for 2025, will be the mission that lands humans on the Moon's surface. However, due to some challenges, the schedule has been delayed. The Moon is not the final destination. According to NASA's plans, it will serve as a stopover for refueling on the way to Mars. NASA is currently testing Mars-like living conditions in Texas, USA. From June 2023, 4 volunteers have been part of a year-long simulation, acting as real astronauts. At the same time, Elon Musk's SpaceX has set its sights on sending humans directly to Mars for settlement. However, this remains a hypothesis, as the million-year journey of humanity carries countless unpredictable factors. The language of future Earth inhabitants may be radically different from what we know today. The spacecraft's journey log might become a valuable ancient document, symbolizing a once thriving civilization from the past. Although the lifespan of the crew is limited around 60 years for some, with a few lucky members possibly living an additional 15 years, a 56-year journey would make it possible for humanity to undertake a round trip to the Andromeda Galaxy, the closest galaxy to the Milky Way. This journey would allow us to witness another galaxy firsthand, even if some crew members may not make it back. When returning to Earth after 5 million years, if humanity no longer exists, the planet may have undergone significant recovery. Nature will regain control, and biodiversity might return to a state reminiscent of Earth before humans. The crowded cities would disappear, replaced by vast forests and coral reefs stretching across the oceans. To undertake journeys beyond Andromeda, extending lifespan is essential. Scientists from the Mayo Clinic have developed a method to extend the lifespan of mice by 35% without causing significant side effects. If successfully applied to humans, the average lifespan could increase from 71 to 95 years. This technology works by removing old, weakened cells that no longer have the ability to divide. This helps delay age-related diseases such as cardiovascular disorders, kidney failure, and cataracts. Old, weakened cells appear throughout the body over time, from the skin and muscles to the internal organs. These cells function like an emergency brake to prevent further cell division, reducing the risk of cancer. However, when the number of these old cells increases too much, they become a burden on the body. When people are younger, the immune system regularly removes damaged cells from the body. However, over time, this function weakens, causing damaged cells to accumulate in organs, leading to significant harm. Notably, these cells are linked to dangerous conditions like heart failure, arthritis, Alzheimer's, and cancer. To address this issue, researchers conducted gene mutations on laboratory mice to stimulate them to continue producing caspase, an important protein that helps eliminate damaged cells. This protein is only activated to respond to p16 proteins produced by the old cells. The research process included adjusting caspase using a special drug. Middle-aged mice were injected twice a week throughout their lifetimes. The results showed that the lifespan of the mice was extended by 17 to 35%, and they remained healthier than untreated mice. However, this therapy is not yet perfect. Some old cells, especially those in the intestines and liver, have not been removed, leading to difficult-to-control damage. In the future, researchers aim to develop a method to completely remove aging cells in humans, which is much more challenging than in mice. Unity Biotechnology has invested in this research, hoping to develop a drug capable of eliminating 60 to 70% of the old cells in humans. If successful, lifespan-extending technology will no longer be a dream but a reality, paving the way for journeys beyond the Virgo cluster, where humanity currently resides. The Virgo cluster is located within the Laniakea supercluster, a vast region of space stretching across millions of light-years, containing tens of thousands of galaxies. A round trip beyond this galaxy cluster would take about 76 years at the spacecraft's maximum speed. During the journey, the Lorentz factor would reach 250 million. Upon returning to Earth, the time difference between the spacecraft and the home planet could make it unrecognizable. Continents would have shifted from their original positions, plants and animals would have vanished, the air would become unbreathable, and Earth would be left with only traces of a once thriving world. The Sunday's brightness would increase by nearly 10%, accelerating the weathering process to a severe level. The reduction in CO would prevent plants from photosynthesizing, leading to the complete collapse of the ecological chain. If fortunate, we might find a few simple microorganisms still alive. In this return, humanity would surely feel sorrow upon witnessing Earth, once a vibrant home, now a planet slowly running out of life. To forget the grief of returning to Earth, another option would be to never return. Laniakea is not the edge of the universe, and we could travel further. Thanks to time dilation, we could journey even farther at an exponential rate year by year, using a spacecraft that achieves 1g acceleration. However, can humans reach the edge of the observable universe? Sadly, the answer is no. The vast distances of billions of light-years, combined with the ever-increasing expansion of the universe, make it an insurmountable challenge. In 1998, astronomers used telescopes to observe distant supernovae and study the expansion rate of the universe. they discovered that not only is the universe expanding, but it is also accelerating. This phenomenon, believed to be caused by dark energy, causes the distance between regions of space to grow increasingly larger. Based on measurements, the farthest distance light has traveled since the Big Bang, 13.8 billion years ago, is approximately 133.8 billion light-years. However, due to the expansion, this distance is actually 46 billion light-years. When we exit the gravitational pull of the superclusters, our spacecraft would be directly affected by the expansion of the universe. This would make the journey progressively more difficult. Scientists have calculated that the furthest boundary humanity could reach if they still wish to return us about 8.3 billion light-years. If we surpass this boundary, we would be trapped in the void forever, as the expansion rate of the universe is much greater than the speed of light. If this is a one-way journey, what will await humanity beyond the 8.3 billion light-year boundary? The current answer is nothing. As we continue to accelerate over the course of 200 years, time on Earth would have passed 10 circumflex 41 years. This is enough time for even protons, in theory, to completely disappear. Thus, our journey would end at the farthest point where there is neither time nor space. But even here, no conclusions are ever final because science is constantly evolving. A few centuries ago, humanity believed the Earth was flat and the center of the universe. But now, science has opened up boundaries we never imagined. Who knows? With a few scientific breakthroughs, the universe may no longer be as mysterious in the future. The question arises, if all ultimately leads to nothingness, is exploring the universe still meaningful? Perhaps this is something to leave to scientists, those who truly understand their goals. Whether humanity achieves its dream of space exploration as we know it today or not, one thing is certain: human ambition will always drive civilization further.
In the vast universe, humans have discovered many strange planets, each with features that ignite the imagination. Some planets are covered in oceans of molten lava, burning like an eternal flame in the cold expanse of space. Others experience winds faster than the speed of sound, creating unending storms. There are even planets made of diamond, shimmering brilliantly under the faint light of their parent stars. These discoveries not only expand our understanding of the cosmos but also spark hope for finding life beyond Earth, fueling dreams of conquering distant, unknown worlds. Number 1. HD 189733b, the planet of glass rain. HD 189733b is one of the most fascinating and mysterious exoplanets ever discovered. Located about 63 light-years away from Earth in the constellation Vulpecula, this gas giant stands out among thousands of other planets due to its extraordinary feature, incredible glass rainstorms. At first glance, HD 189733b appears deep blue, reminiscent of Earth when viewed from afar. However, this color is not a sign of water or life but the result of light reflecting off silicate particles in its atmosphere. As a hot Jupiter, HD 189733b orbits extremely close to its parent star, causing surface temperatures to soar to an extreme 1000 degrees Celsius. The planet's atmosphere is rich in silicates, a compound responsible for its bizarre weather phenomenon, glass rain. At such high temperatures, silicates vaporize and dissolve into the atmosphere. As they move through cooler atmospheric regions, they condense into tiny glass particles. However, the rain on HD 189733b is unlike the rain on Earth, where droplets fall straight down. Instead, these sharp glass particles are blown horizontally by ferocious winds reaching speeds of up to 8,700 km per hour, faster than the speed of sound. This glass rainstorm is not just a visually striking weather event but also a deadly and perilous phenomenon, HD 189733b is a vivid testament to the diversity and strangeness of the universe. It challenges all our limits of understanding regarding weather, geology, and planetary conditions. Discoveries about this planet not only broaden our perspective on worlds beyond the solar system but also ignite a deep desire to explore the unknown corners of the cosmos. Every mystery unraveled from HD 189733b reminds us that this vast universe is brimming with wonders waiting to be revealed. Number 2. Kepler 10c, Godzilla of Super-Earths. Kepler 10c, nicknamed the Godzilla of Super-Earths, shocked the astronomical community upon its discovery. Located about 560 light-years away from Earth in the Draco constellation, this exoplanet stands out not only for its immense size and mass but also for what it reveals about planetary formation and evolution in the universe. Kepler 10c has a radius 2.3 times that of Earth but a mass exceeding 17 times. This places it in the category of super-Earths, planets larger than Earth but smaller than gas giants like Neptune. However, the most striking feature of Kepler 10c lies in its composition. Contrary to initial expectations that it would be a gas planet, Kepler 10c is a rocky planet with a core composed of heavy elements. This challenges the previous understanding that planets of such size and mass would have thick gaseous envelopes and resemble miniature Jupiters. Kepler 10c orbits its host star closely, completing a full orbit in just 45 days. While it resides in an uninhabitable zone due to its high surface temperature, the planet continues to astonish scientists for another reason: its age. The Kepler 10 system formed approximately 11 billion years ago, during the early days of the universe. This suggests that the heavy elements required for the formation of rocky planets were present much earlier than previously believed. Kepler 10c is more than just an extraordinary discovery, it fundamentally reshapes our understanding of planetary formation and evolution. Its nickname, Godzilla of Super-Earths, reflects its uniqueness and dominance among planets of its kind. Research on Kepler 10c raises new questions about the potential existence of similar massive planets and their role in the history of the universe. This planet serves as a powerful reminder that even the most well-established scientific theories must sometimes yield to the surprises of the cosmos. Number 3. WASP-12b, the Devoured Planet. WASP-12b is a gas giant exoplanet with a unique and alarming fate. It is being devoured by its parent star. Located approximately 1,410 light-years from Earth in the constellation Auriga, WASP-12b provides a dramatic glimpse into the harsh destinies of planets orbiting too close to their stars. WASP-12b belongs to the category of hot Jupiters, with a mass about 1.4 times that of Jupiter and nearly twice its size. However, its defining characteristic is its extreme proximity to its host star, just 3.4 million kilometers away, far closer than Mercury is to the Sun orbiting its star in an incredibly short period of 1.1 Earth days. WASP-12b endures intense gravitational and thermal forces. This proximity subjects WASP-12b to scorching surface temperatures of up to 2,500 degrees Celsius, sufficient to destabilize its atmosphere. The immense gravitational pull from its parent star has stretched the planet into an egg-like shape, deviating from the typical spherical form of planets. This same gravitational force is also responsible for the ongoing erosion of the planet's mass. Studies reveal that WASP-12b is losing mass at an astonishing rate of approximately 6 million tons per second. Gas from the planet's atmosphere is being siphoned off by the host star, forming a swirling disk of material around it, much like how a black hole accretes matter from nearby stars. Scientists estimate that within a few million years, WASP 12b will be completely consumed by its star, leaving only remnants of its once massive presence. WASP 12b stands as a vivid demonstration of the destructive power of gravity and stellar radiation. This planet not only enhances our understanding of the fate of hot Jupiters but also raises profound questions about the evolution of planetary systems across the universe. WASP 12b serves as a stark reminder that the cosmos is not only a creator of worlds but also a destroyer of the very planets it gives birth to. Number 4. Trace 2b, the darkest planet. Trace 2b, an exoplanet classified as a hot Jupiter, is renowned as the darkest planet ever discovered. Located about 750 light-years from Earth in the Draco constellation, Trace 2b intrigues astronomers with its ominously dark appearance and the mysteries surrounding its composition and physical phenomena, similar in size to Jupiter, with a diameter 1.2 times that of the Solar System's gas giant. Trace 2b orbits its host star at an extraordinarily close distance of just 5 million kilometers, much closer than Mercury is to the Sun. This proximity results in searing surface temperatures of up to 1,100 degrees Celsius. The planet's most striking feature, however, is its exceptionally low reflectivity. Scientists have found that Trace 2b absorbs over 99% of the starlight that hits it, making it the darkest planet known to date. By comparison, it is darker than coal or black ink on Earth. The faint amount of light reflected by Trace 2b is so dim that it is nearly impossible to observe with the naked eye. The reasons behind Trace 2b's darkness remain a mystery, though researchers have proposed several hypotheses. One suggests that the planet's atmosphere contains unusual chemical compounds, such as vaporized sodium, potassium, or titanium oxide, which are highly effective at absorbing visible light. Furthermore, the planet lacks the reflective cloud cover seen on Jupiter, which significantly enhances its ability to absorb light. Despite its extreme darkness, Trace 2b is not entirely devoid of illumination. Due to its high temperatures, its atmosphere emits a faint red glow, akin to the light from smoldering embers. This eerie reddish hue gives the planet an ominous and enigmatic appearance, resembling a floating fireball in space. Trace 2b is not just a unique phenomenon but also raises new questions about the diversity of exoplanets. It demonstrates that in the vastness of the universe, there are not only bright and vibrant worlds but also dark and mysterious places. Trace 2b reminds us of the vast variety of conditions that planets can exhibit, challenging our understanding of planetary systems and their potential extremes. Number 5. GJ1214b, the Water Planet. GJ1214b, known as the Water Planet, is one of the most intriguing exoplanets ever discovered, marking a significant milestone in the exploration of worlds beyond our solar system. Located about 48 light-years from Earth in the Ophiuchus constellation, this planet orbits a faint red dwarf star named GJ1214. Classified as a super-Earth, GJ1214b is larger and more massive than Earth but smaller than Neptune. With a diameter approximately 2.7 times that of Earth and a mass 6.5 times greater, GJ1214b's defining feature is its vast water content, which appears to dominate its composition and structure. Temperatures on GJ1214b range between 200 degrees Celsius and 280 degrees Celsius, making liquid water unlikely. Instead, water exists in exotic forms such as superfluid or supercritical states due to the extreme pressure and heat. These unusual states include hot ice or supercritical steam, forms of water never naturally encountered on Earth. Another key aspect is GJ1214b's thick atmosphere. Data from the Hubble Space Telescope suggests that the atmosphere is rich in water vapor or enveloped by dense clouds. This atmospheric composition confirms the presence of water but also raises complex questions about the planet's habitability. Although conditions on GJ 1214b are far from suitable for life as we know it, they invite speculation about life forms that might adapt to such extreme environments. GJ 1214b is a testament to the diversity of planets in the universe. Its discovery and study enhance our understanding of how water can influence a planet's structure and climate, even under conditions vastly different from those on Earth. It also ignites hope that we may one day find similar planets where water, in any form, could serve as the foundation for life. Number 6. HD 209458b, Osiris, the comet-tailed planet. HD 209458b, poetically named Osiris, stands as one of the most remarkable exoplanets in astronomical history. Located approximately 159 light-years from Earth in the Pegasus constellation, Osiris is a quintessential, hot Jupiter, yet it captivates astronomers with its rare phenomenon, a comet-like tail formed by gases being stripped away from its atmosphere by its host star, with a mass about 0.7 times that of Jupiter but a size 1.3 times larger. Osiris is a low-density gas giant. Orbiting just 7 million kilometers from its parent star, its surface temperature soars to around 1,000 degrees Celsius. This extreme proximity to the star is the primary cause of its atmospheric loss. The intense gravitational pull of the host star, combined with the relentless heat, forces the outer layers of Osiris's atmosphere to escape into space at a rate of hundreds of thousands of tons per second. Light gases like hydrogen and helium, along with ionized particles, are carried away, forming a massive tail extending millions of kilometers into space, akin to a comet's tail. This phenomenon marked the first-ever observation of atmospheric evaporation on an exoplanet, representing a milestone in the study of planets beyond our solar system. The comet-like tail not only offers a striking visual but also valuable insights into the planet's chemical composition. Further studies revealed the presence of molecules like oxygen and carbon in Osiris's atmosphere, shedding light on the evolutionary processes of planets orbiting close to their stars. Osiris serves as a vivid demonstration of the destructive power that host stars can wield over planets in tight orbits. This planet not only enhances our understanding of atmospheric erosion but also paves the way for new research into the survival and transformation of gas giants in extreme environments. HD 209458b, with its breathtaking comet-like tail, symbolizes the universe's extraordinary blend of beauty and brutality. Number 7. PSRB 125712b and C, planets orbiting a neutron star. PSRB 125712b and C are among the first exoplanets ever discovered, notable for their unique orbits around a neutron star, the incredibly dense remnant of a dead star. Located approximately 2,300 light-years away in the Virgo constellation, this planetary system represents a groundbreaking discovery in astronomy, proving that planets can exist even in the harsh environments surrounding neutron stars. The host star, PSRB 125712, is a pulsar, a type of neutron star that emits regular pulses of electromagnetic radiation as it spins rapidly. This stellar remnant was created by a supernova explosion, where the core of a massive star collapsed into an object so dense that a teaspoon of its matter would weigh billions of tons. PSRB 125712 rotates at an astonishing speed, completing over 1,000 rotations per second and emitting pulses every 6.22 milliseconds. The two planets, PSRB 125712b and C, orbit this pulsar at relatively close distances. The innermost planet, PSRB 125712b, has a mass about 0.02 times that of Earth, less than Mercury, while the slightly larger PSRB 125712c has a mass about 4% that of Earth. Both are rocky planets, orbiting at distances of 19 cents and 36 cents from the neutron star, respectively, closer than Mercury's orbit around the Sun. What makes these planets remarkable is their survival in the aftermath of a supernova explosion. Scientists propose two main hypotheses regarding their origins: either they are remnants of the material left over after the supernova, or they formed from debris accreted onto the neutron star following the explosion. Regardless of their formation, their persistence in the intense radiation field of a pulsar is astonishing. PSRB 125712b and c have redefined our understanding of planetary formation and survival. They highlight the incredible diversity of planetary systems in the universe and serve as a testament to the resilience of planets in even the most extreme environments. These two worlds are a vivid reminder of the surprises the cosmos holds and the ingenuity of nature in crafting its myriad celestial wonders. Number 8. 55 Cancri E, the Diamond Planet. 55 Cancri E, an exoplanet located in the constellation Cancer, is a dazzling and mysterious world often referred to as the Diamond Planet. Situated about 40 light-years from Earth, this planet stands out not only for its unique composition but also for its extreme conditions, which far surpass anything seen in our solar system. Belonging to the super-Earth category, 55 Cancri E has a radius twice that of Earth and a mass approximately 8 times greater. The planet orbits its host star at an incredibly close distance of just 0.015 Australian dollars, about 1/25th the distance between Mercury and the Sun. As a result, it completes an orbit in a mere 18 hours. With surface temperatures reaching a scorching 2,400 degrees Celsius 4,352 degrees Fahrenheit, hot enough to melt most types of rock, what truly sets 55 Cancri E apart is its chemical composition. Scientists hypothesize that the planet contains a high proportion of carbon, possibly including vast quantities of diamond. Under extreme pressure and temperature conditions, carbon in the planet's core could crystallize into diamond, potentially comprising a significant portion of its mass. If these assumptions are correct, 55 Cancri E might possess diamond reserves tens of times greater than all of Earth's combined. The planet's atmosphere adds another layer of intrigue. Observations from the Spitzer Space Telescope suggest the presence of a thick atmosphere containing hydrogen, helium, and possibly cyanide, a toxic gas that makes the environment highly inhospitable to life as we know it. Recent studies also propose that 55 Cancri E might experience superheated volcanic activity, with eruptions ejecting material from its molten surface. 55 Cancri E exemplifies the extraordinary diversity of exoplanets, stretching the boundaries of human imagination. Although the Diamond Planet hypothesis remains unconfirmed, ongoing research continues to expand our understanding of how planets form and evolve under extreme conditions. This shimmering, enigmatic world is not only a testament to the richness of the cosmos but also a symbol of its unyielding capacity to surprise and inspire us. Number 9. K2-141b, the Planet of Fire and Ice. K2-141b, a unique and extreme rocky exoplanet, lies about 200 light-years away from Earth in the constellation Pisces. As a super-Earth, K2-141b is approximately 1.5 times the size of Earth and 5 times its mass. However, what sets this planet apart is not just its size but its extraordinary climate and geological conditions, orbiting extremely close to its host star, at a mere distance of 1.5 million kilometers, about 1/150 the distance between Earth and the Sun. K2-141b is tidally locked. This means one side of the planet permanently faces the star while the other remains in perpetual darkness. Such an arrangement creates two drastically opposing environments, a blazing day side and a freezing night side. The day side of K2-141b is a fiery inferno, with surface temperatures reaching up to 3,000 degrees Celsius (5,432 degrees Fahrenheit), hot enough to vaporize rock. Elements like sodium, silicon monoxide, and silicon dioxide are turned into gas, forming a rock vapor atmosphere that envelopes the planet. Supersonic winds, potentially reaching speeds of 5,000 kilometers per hour, 3,107 miles per hour, transport these vaporized minerals from the day side to the night side. On the night side, temperatures plummet to an icy -200 degrees Celsius (-328 degrees Fahrenheit), causing the rock vapor to condense and fall back to the surface as rock rain. The solidified minerals on the night side may then flow back toward the day side through molten lava streams, creating a closed-loop cycle akin to Earth's water cycle, except it operates with rocks and minerals instead of water. The perpetual contrast between K2-141b's scorching day side and its frigid night side, combined with the fascinating cycle of rock vaporization and solidification, makes this planet a compelling subject for study. It offers a rare glimpse into how rocky planets can form and persist under extreme conditions far beyond our solar system. K2-141b stands as a vivid testament to the diversity and harshness of worlds in the universe, showcasing the extremes of planetary science and expanding our understanding of the possibilities for planets beyond our imagination. Number 10. Gliese 581c, a candidate for life. Gliese 581c is one of the most notable exoplanets in the history of space exploration, often considered a promising candidate for extraterrestrial life. Located approximately 20.4 light-years away in the constellation Libra, it orbits its host star Gliese 581, a red dwarf with a much cooler temperature compared to our Sun. As a super-Earth, Gliese 581c is about 1.5 times the radius of Earth and 5 times its mass. Its rocky composition and stronger surface gravity distinguish it as a potential haven for life. Completing an orbit around its host star in just 13 days, it resides within the so-called habitable zone, a region where liquid water could theoretically exist due to the planet receiving similar levels of radiation as Earth gets from the Sun. However, a notable feature of Gliese 581c is its tidal locking, meaning one side of the planet is perpetually facing the star while the other side remains in constant darkness. This leads to extreme climatic contrasts. The day side might be too hot for life to survive, while the night side could be frigid enough to freeze water. The transitional area, known as the twilight zone, where temperatures are more moderate, presents the most viable conditions for liquid water and potentially life. The planet's atmosphere, if present, plays a crucial role in determining its habitability. A sufficiently thick atmosphere could redistribute heat more evenly between the day and night sides, mitigating the harsh temperature extremes. However, the exact composition and presence of an atmosphere on Gliese 581c remain unknown, as current observations have not yet provided definitive data. Gliese 581c was once a beacon of hope in the search for life beyond Earth. Despite debates about the planet's actual conditions, it symbolizes the potential of exoplanetary research. By studying worlds like Gliese 581c, we continue to broaden our understanding of habitable zones and the diverse conditions under which life might emerge. This planet remains an enduring emblem of humanity's quest to discover other hospitable worlds in the vast cosmos.
In 1823, astronomer Heinrich Olbers posed a seemingly simple but deeply philosophical question. Why is the night sky dark when the universe is believed to be infinite? and filled with the light of countless stars? According to theory, if the universe is truly infinite and contains an infinite number of stars, then the sky should be bright with light, not as dark as we observe it to be. This question led to Olbers's paradox, an important scientific problem in astronomy. This paradox was not truly solved until 1929, when Edwin Hubble discovered that the universe is not static but is expanding. This means that the light from distant celestial bodies is redshifted and becomes weaker over time, making the night sky appear as dark as we observe it. However, this discovery opened up another question. If the universe is constantly expanding, then what is its actual size? Is the universe finite or infinite? This is one of the central questions of modern physics. Looking back at history, people have had many misconceptions about the universe. In ancient times, we believed that the Earth or the Sunday was the center of the universe. In the 16th century, Copernicus and Kepler broke this concept, proving that the Earth was just a planet orbiting the Sunday. In 1838, astronomer Friedrich Bessel continued to revolutionize human understanding when he first measured the distance to a star using the parallax method, determining the distance to the star 61 Cygni to be more than 10 light-years. In the 1920s, the debate between Harlow Shapley and Heber Curtis about the nature of distant nebulae laid the foundation for a major turning point in our understanding of the universe. Later, Edwin Hubble proved that those nebulae were actually independent galaxies, not just gas clouds in our Milky Way. This greatly expands the range of human observation, leading to the concept of the universe being vast beyond imagination. With the development of telescope technology, scientists today can observe celestial objects more distant than ever before. One of the most important discoveries is the galaxy GNZ11, one of the brightest and most distant galaxies ever observed, with light emitted about 13.4 billion years ago. This means that when we see GNZ11, we are looking into the early universe, when it was only a few 100 million years old. The estimated distance from Earth to this galaxy is up to 32 billion light-years, a number that exceeds the time it takes light to travel due to the constant expansion of the universe. The discovery of GNZ11 not only provides insight into the formation of galaxies in the early stages of the universe, but also raises new questions about the evolution of space and time. If GNZ11 is 13.4 billion years old, and the universe is thought to be 13.8 billion years old, could there be even more distant and older galaxies? This is a question that scientists are trying to answer. New space telescopes, such as NASA's James Webb, are expected to provide important clues that will help us better understand the true nature of the universe and whether it is finite. The universe is not simply a vast expanse of space, but also a dynamic picture of constant evolution. Each advance in astronomical observations opens up new mysteries that challenge our current understanding of the nature of space, time, and matter. Is the universe truly infinite, or just part of a larger reality? In the process of exploring the universe, two important concepts need to be clearly distinguished: the observable universe, or visible universe, and the visible universe. These two concepts are not limited by the observational capabilities of telescopes, but by the nature of space-time. The observable universe is defined as the spatial range that includes all objects and phenomena that can be observed at the present time by scientific means. According to current calculations, the observable universe has a radius of approximately 45 billion light-years, equivalent to a diameter of about 90 billion light-years. However, this limit is not the actual size of the universe, but the farthest distance that light from the first objects can travel to Earth since the formation of the universe. Meanwhile, the visible universe is defined as the part of the universe that can be directly observed by light and other forms of radiation. This range is slightly smaller than the visible universe due to the characteristics of the first stage after the Big Bang. In the first hundreds of thousands of years, the universe was too hot and dense, preventing light from spreading freely due to the blocking of ionized plasma. Only when the universe cooled and the plasma dissipated during the reionization period did light begin to flow freely. Observations of the observable universe have raised fundamental questions about the nature of space. Is the universe truly infinite, or is it positively curved like a giant sphere? If the universe were truly curved, we would see the same galaxy in two different shapes from opposite directions. However, studies of the cosmic microwave background, CMB, emitted when the universe was only 380,000 years old, have found no evidence that the universe has a repeating structure. To date, scientists have found no evidence that this is the case. However, these discoveries have revealed that the observable universe is not simply an infinite void, but a complex structure affected by the expansion of space-time. This confirms that, although humans have made great strides in exploring the universe, there are still countless things that have not been solved. Questions about the nature of space, time, and what exists beyond the observable universe continue to challenge, stimulate curiosity, and urge people to explore endlessly. The observable universe is extremely large, with a radius of about 45 billion light-years, equivalent to a sphere with a diameter of approximately 90 billion light-years. However, the question of the true size of the universe remains a mystery. Does the universe extend far beyond our observation range? Is it infinite, or is there a certain limit that we cannot yet identify? An important assumption in cosmology, the cosmological principle, states that when observed at a large enough scale, the universe will look the same from every location. This means that if someone were to live in the distant galaxy GNZ11, they would see a sky similar to what we see from Earth. In this way, what we see is not something special, but just a part of the overall picture of the universe. Suppose that the inhabitants of the galaxy GNZ11 could observe the universe from their perspective. Would they see a completely different reality than we do? That does not mean that they would encounter a physical boundary of the universe. If a physical boundary exists, it has not yet been discovered by humans. Some theories also suggest that the universe may have a curved spatial structure, similar to a sphere, and if this is true, then a galaxy could appear to be in two opposite directions in the universe, while actually being one. To make it easier to visualize, imagine two people A and B at opposite ends of the observable universe. When they look out, they may be looking at the same galaxy from opposite directions, but because of the great distances, they cannot communicate with each other to realize this. So, although there is no evidence that the universe repeats itself, we cannot use the cosmological principle to determine the true size of the universe. The only thing we can say for sure is that the observable universe is about 90 billion light-years across, but the reality may be much larger than what we can see. In addition to the cosmological principle, an important way to estimate the size of the universe is to analyze its spatial curvature. This curvature is determined through observations of the cosmic microwave background, CMB, an ancient form of radiation emitted from the very beginning. When the universe was only 380,000 years old. If the universe has positive curvature, similar to the surface of a sphere, then parallel lines in space should gradually converge at a point. Just as two people walking straight towards the North Pole on Earth will eventually meet. Conversely, if the universe is flat, parallel lines should stretch on forever, without ever intersecting. Studies based on data from the European Space Agency's ESA, Planck spacecraft and experiments such as Boomerang have shown that the universe is almost flat, with an infinitesimal margin of error. This implies that if the universe has curvature, it is too small to be detected by current methods. An important conclusion from this is that the universe may be infinite, or at least much larger than we can observe. In addition to the flat or spherical universe model, some theories suggest that the universe may be shaped like a torus, like a giant donut. In this model, if one travels far enough in a given direction, one can return to the starting point without ever realizing that one has crossed any boundary. This means that the universe is both finite in size and has no boundaries in the conventional sense. In 2012, a team in France used a supercomputer to simulate the geometry of a two-dimensional torus-shaped universe embedded in three-dimensional space. The results showed a complex geometry that still obeyed the rules of flat space, reinforcing the possibility that the universe may be finite but closed. The idea of an infinite universe is not just a theoretical question, but also has profound philosophical consequences. One of the key paradoxes that arises from this hypothesis is that if the universe is truly infinite, then every physical possibility can occur, and not just once, but countless times. This raises the strange prospect that there could be infinite versions of ourselves in distant regions of the universe, with lives that are almost identical, but differ in a few small details. This is part of the so-called infinite paradox, a problem that has troubled physicists and philosophers for decades. For some scientists, a simpler explanation is to accept that the universe is indeed finite, even if it is closed in ways that we cannot yet directly observe. If the universe is indeed a torus, or even a more complex shape, then the limits of space may not be what we see. However, a number of other theoretical models offer different approaches to the problem of the size and nature of the universe. One of the most prominent is the eternal inflation model, in which our universe is just a bubble of space in an infinitely vast sea. According to this model, our universe went through a period of inflation, a very rapid expansion immediately after the Big Bang. When this ended in our region of space, the universe entered a state of slower expansion, similar to what we observe today. However, beyond the boundaries of the observable universe, inflation continued in other regions, creating countless new bubble universes. These bubble universes could have completely different physics, where the physical constants, even the fundamental laws of nature, might not be the same as ours. However, even this model cannot help us avoid the problem of an infinite universe, because if there are an infinite number of such universes, then the repetition of physical configurations and infinite possibilities would still occur. This leads to an ontological crisis, as we are faced with the consequences of infinity. If the universe is truly limitless, then it means that every possible physical configuration will occur, not just once, but an infinite number of times. Under this scenario, there could be an infinite number of versions of each of us, living similar lives but differing in some small details. This repetition raises profound philosophical questions about the uniqueness of reality and the true nature of space-time. Some scientists have sought to escape this paradox by proposing that there may be an ultimate limit to the universe, where the nature of space changes, or where there is a specific end. However, such hypotheses remain in the realm of theory and have not been confirmed by any experimental evidence. So whether our universe is finite or infinite remains a great mystery. If it is infinite, we are faced with profound questions about the nature of reality. If it is finite, what lies beyond its boundaries? No matter how many theories have been proposed, each model seems to encounter paradoxes and limitations that current science cannot resolve. This suggests that the story of the universe is not over, and future discoveries could completely change the way we understand reality. What do you think? What is your view of the universe and its vastness? Let me know in the comment section of the video.